All right. Good morning, and thank you for joining us today. The webinar will begin momentarily. I just wanted to let you know that additionally to the chat function, you can also submit questions via the Q&A. Today's webinar will be recorded and a link will be sent out to all participants. Your host today is Kevin Sidner, and so let's begin.
Hi everyone, welcome to this edition of the IAV webinar series. My name is Kevin Sidner and I'm responsible for powertrain calibration at IAV in the USA. You can contact me at IAV via the email address kevin.sidner@iav-usa.com shown on screen, or via our general email info@iav-usa.com. In today's webinar, I will be covering the topic of model-based calibration, specifically the Advanced Boundary Finder. This portion is the third part of our webinar series focusing on model-based calibration, specifically on dynamic DOEs. In summary, this is an introduction to the Advanced Boundary Finder method. I will start with a short recap of the previous webinars on dynamic DOE, introduce the Advanced Boundary Finder, discuss its setup and functionality, and finish with a summary. Today's presentation will last around 10 minutes. During the presentation, we will keep the chat function found at the bottom of your screen open for questions. At the end of the presentation, there will be a 10-minute session to address your questions. Also, please look for more webinars in this series. Details can be found on our Twitter page at twitter.com/IAV_USA. I will start the presentation with a short 1-minute video introducing IAV, so please continue to watch and I hope you find this webinar interesting.
IAV expertise can be found all over the road. There's no such thing as an IAV car, but almost every passenger car utilizes IAV technology. For instance, in the chassis, in drive mechanisms and engines, in the vehicle's electronics, in body structures, and in its safety systems. IAV develops innovative solutions for the entire vehicle and for almost every automobile manufacturer. IAV also has state-of-the-art facilities for testing everything on wheels, whether passenger car or commercial vehicle, fuel-powered or electric. Exciting activities covering every part of the vehicle. That's IAV.
Now that you've learned a little bit about IAV, let's get started with today's topic, Advanced Boundary Finder. Let me give you a short overview of model-based calibration, in case you did not have a chance to attend the previous webinars on dynamic DOE for model-based calibration. To calibrate a model engine with its multiple control functions, it's important to optimize all control variables for the desired target values. This includes, for example, fuel economy or specific emission constituents. Model-based calibration allows for a multi-objective optimization and a good understanding of the trade-offs between fuel economy, emissions, and durability. This is a quick recap of the DOE methods covered in the previous webinar. As you can see, the standard calibration method is time-consuming if you have a high number of parameters. Steady-state and dynamic DOEs allow for a significant reduction in measurement time and a true multi-objective optimization. Dynamic DOEs also offer the benefit for understanding of the transient behavior. The Advanced Boundary Finder method can be used for both the steady-state and the dynamic DOE methods. The dynamic DOE calibration process starts with identification of the engine, including the operating range and the drive cycles. The next step is to define the boundaries of engine operation. This can be done efficiently with the Advanced Boundary Finder, where we will focus on today. The Boundary Finder allows us to generate the convex hull, limiting the test space to the reachable areas of engine operation. Where the setup process for the dynamic DoE differs is the setup of the test plan. Instead of defined points arranged in a grid like in a traditional calibration method, or predetermined steady-state points that capture multiple changes in variables in a steady-state DoE, the test plan is instead comprised of a set of sinusoids of the respective calibration variables. This is why predetermining the hull beforehand is so important, since it limits the test space to the reachable areas and ensures that the calibration variables are varied in a useful space for the model. Once the setup has been completed, we need to scale the test plan to the generated hull and then execute the testing on the test bench. Once the test data has been captured, we can generate the engine system models and use them to calibrate the engines or develop our control system. One of the challenges in any DoE is the determination of the design space and engine constraints. The ranges in which parameters can be varied based on the constraints of the engines are likely unknown in the beginning. Assumptions can be made, but it's hard to judge with a large number of calibratable parameters on a modern engine. Additionally, in some cases, the limits of the actuators may be unknown. The Advanced Boundary Finder allows to measure the engine constraints beforehand using an automated procedure in a test cell. These results are then implemented in the design of the experiment. This allows the design space to be constrained to only the reachable area of the engine operation. This not only improves the model quality, since all design points are usable, but also the efficiency of testing, since attempts of measuring unreachable points can be eliminated. In summary, the Boundary Finder allows the definition of engine constraints without detailed knowledge of the system. The Boundary Finder method is run automated at the test bench before the DoE test plan is designed. Limits can be defined based on the need of the experiment, but usually include items like maximum cylinder pressure, knock, temperatures, or turbine speed. First, the extreme corners of the test space are targeted, starting from an initial safe point. If one or more of the target points cannot be reached, the first portion of the hull is generated. As you can see in the highlighted area, the test point indicated by the pink triangle was targeted but could not be reached. The reachable point, indicated by a red circle, is used to define the first part of the hull. From there, successive iterations will target the surface normal of the largest hull segment, as can be seen in the second and third iteration above. After a few iterations, a close approximation of the actual system boundary is generated and can be used as a design space for our experiment. In summary, the Boundary Finder method can quickly define the test space with very few iterations that are automatically executed at the test bench. In summary, the Advanced Boundary Finder allows the automated definition of parameter limits, actuator limits, and limits in the engine operation. The advantages for the DoE are a better distribution of measurement points. This allows for more measurement points near the optimal engine operation and less measurements with unstable or limit engine operations. All this will lead to improved model quality for our static or dynamic DoE models, since the test space will be well defined before testing. This was the third presentation of a series on model-based calibration. We will cover calibration optimization examples in one of the next webinars. You can find the previous webinars on our IAV Automotive Engineering YouTube channel. Also, look out for more webinars. They will include topics such as pre-PVE automation with IncaFlow, mill-sill-hill simulation with Velodyne, virtual field testing approach, robust OBD calibration, and hybrid emissions model. For a complete list of topics, please visit IAV.com. I want to thank everyone for the interest in IAV and our capability in model-based calibrations. Also, thank you for your questions. If you would like to discuss these topics in more depth, then please feel free to contact me via the email address kevin.sittner@iav-usa.com shown on screen, or via our general email info@iav.com. iav-usa.com. Also, please look out for more webinars in this series. Details can be found on our Twitter page. Now that we've concluded this presentation, let's take some time to answer your questions.
All right, thank you everyone for attending the webinar. I hope you found this somewhat interesting and maybe useful for you for your work. If you have any more questions, just please either type them in the chat or in the Q&A box on Zoom. I got a couple here. Is it required to run the boundary finder for a dynamic DoE? It is actually not. You can also define your limits beforehand if you already know what all the limits and the bounds of the actuator or the engine operation are. So it certainly doesn't have to be used. But in a lot of cases where we use dynamic DOEs or DOEs, we don't know all the engine parameters. Because we are most likely calibrating a new engine or a new system where we don't have the full knowledge. So therefore, it's generally useful to use the boundary finder method, run it on the test bench because it's relatively quick to find out what the actual operation boundaries are. And with that, we can design a better test. It's sometimes even useful when we think the boundaries are known, but some actuators basically max out their control authority before they've reached the full parameter that they can be controlled as. I got another question here just now. Thank you for that, Eduardo. Does the DOE boundary finder search a boundary under steady state conditions or transient conditions? So the boundary finder does it under, I would say steady state conditions, but the way it actually runs, it tries to slowly approach the point that we've defined as the I guess extreme limit. So with that, the parameter is continuously varied or ramped depending on how it's set up. And then once it reaches the boundary, it will no longer progress, or we reach some sort of engine limit, then we will define that steady state point as our boundary. I hope that kind of answers your question. And I got another one. Is it limited in the number of calibration variables, or is there an ideal number? So there's no hard limit, but we have found that in a lot of cases, it makes sense to kind of limit it to a few variables. So you can map each boundary for each actuator or each calibration variable somewhat independently, but they can be all combined into one test plan and all run basically together, even though if they are not simultaneously all varied at the same time. Is there any more questions? If yes, please post them. If not, maybe talk a minute about the setup a little bit more. So the only thing that needs to be defined is basically the initial starting point that's considered safe. And from there, it will run completely automated at the test bench. So very limited knowledge of what we're trying to calibrate is needed beside the initial start point, and then the automated process will take it from there and do the rest. All right. If you have any more questions, just please let me know. I'll probably stay on here for a couple more minutes if you have any questions. If you don't, thank you again for your interest. And if questions come up later, please feel free to just reach out to me. I got another question, Eduardo, thank you. A quasi-static method. So wouldn't the boundary be determined in such a way to be potentially harmful for the engine in some transient combinations? That's theoretically possible, but most times we use it. Let's say we want to, maybe I'll give you an example. Let's say we have a external EGR system and we don't quite know what the engine behavior will be with different EGR levels, or we don't know how much flow we will get with the actuator. So we would probably use the boundary finder to map both of these things at the same time. So we can say, okay, when the valve opens in these conditions, we get X amount of EGR flow, and the engine will only accept EGR percentage of, let's say, 20% before combustion becomes unstable. We would map that semi-statically, and then when we run the dynamic test, the conditions that we reached should still be in that range. So if we don't go outside of that actuator range, it should still be safe for the engine in all these operating conditions. There might be in maybe, if it's not EGR, there might be an overshoot or something of a controller that can still cause that you go outside of these bounds. But during the DoE, we still have all the safeties for the engine active. So once you reach some unstable or potentially unsafe operating condition, the actual experiment where we measure the test data will still catch that case and still prevent the engine from being damaged. It's just in most cases when that happens a lot, it's obviously protected. It tends to expand the testing time that we need, because each time we hit such a boundary, we will need to go back to a safe space and attempt a different point with slightly less extreme values. All right, I got another question in the meantime from Shahab, thank you. Does the dynamic DoE work with specific types of dynos? Is there any specific requirements on the dyno? So yes, for the dynamic DoE, you need to have a dyno that has fast transient capabilities, and you need to be able to have a fast connection to, first of all, your general sensors and also the control of your engine. So you need a high-speed connection generally to the ECU, between the dyno and the ECU, to make the changes as transiently and as dynamically as you want. And you need, on the other side, to be able to record it in the same resolution that you're making these changes. So requirements are basically, if you have a modern test cell and a high-speed connection to the ECU, it's possible. All right, I'm not seeing any more questions at the moment. Thank you again. Feel free to reach out. We have some more webinars coming up. I think there's also some more on dynamic DoE. You can find the previous ones on our YouTube channel if you're looking for them. We will post them there. And oh, we got another question. The data acquisition, how fast does it have to be? There is some variance of how fast we dynamically can change these parameters. 10 Hertz is usually good. We usually try to be a little faster to measure every millisecond, something like that during these tests, but it can be somewhat adjusted. All right, well, thank you again, and I hope to see you for one of the upcoming webinars as well.
Thank you, and goodbye, everyone. Have a good day.
Bye-bye.